So, good morning, everyone. I will start now my presentation on a topic which considers an epidemic model, a mathematical model for the spread of an epidemics. And I will explain what is the modification of the classical SIR model, where I introduce also vaccination and several levels of immunity. So let's start with the basic SIR model. This is a compartment model. Let's assume we have a population which is scaled to be of size 1, and we divide it into several compartments. This is the classical model in epidemiology: susceptible, infected, and recovered. And we have the following system of ordinary differential equations which models the spread of this epidemic. So the susceptible population gets infected by contact with infected ones at this rate beta. Infected individuals come into this compartment by moving from the S compartment, and after some time they recover. So alpha is the recovery rate, and they go out of the infection state and get into the new state recovery, and this is the simplest model. Now we can assume for the parameters alpha is the inverse of the average time spent in the infectious state, and the beta parameter, this transmission rate, can be written as the product between the reproduction number, which normally depends also on time, but you have also the basic reproduction number R0, you know, from the COVID-19 pandemics, what is the meaning of this basic reproduction number R0. Typically, if it's larger than 1, the epidemic spreads out. If it's less than 1, it will die out. So this is the reproduction number, and its meaning is that is the average number of further secondary infections produced by contacts with one infectious individual. So let's model additional effects. Of course, the motivation is mainly due to the COVID-19 pandemics from the last years, and also some vaccination effects. So we assume that the vaccination delivers only a temporary protection from infection. So it's not a total protection, but lasts only some time. Assume that some individuals get full immunization either by vaccination or by recovery from infection, but this full immunization doesn't last forever, so it will decay in time. We assume that it will decay stepwise, so not all at once. It decays on several levels, and so we assume that this immunity will decay from the maximum level M to the 0 level, which is no immunity, in several steps. Now let's assume that on this level K we have the infection rate beta K vaccination rate, so we can assume that we vaccinate also people with partial immunity but not those with full immunity, and of course the rate of immunity decay eta K. Now let's assume also something about the vaccination rate. We can make two assumptions. That it is also proportional to some power, or it depends also on the number of infected individuals. So we assume that if the infection is very widespread, then people will have high interest in vaccinating themselves. Otherwise, if the epidemic is almost died out, then the people don't have any interest to vaccinate. They don't realize that the epidemic is going on around them. That's why I make also this assumption. And you have also typical cases. You can also assume that there is no vaccination. If you set this parameter equal to 0, then if this power p is not 0 but is larger than 0, still less than 1, then it will be proportional also to the size of the infected population to this power p. And if you assume p equal to 0, then we set this term equal to 1. And then we have also possibility of having vaccination independent of the size of the infected population. So this would be two different cases. This one, where the vaccination is independent on the size of infected population, and if it's dependent, or even if you have no vaccination, but these first two examples can be grouped into one single case. So this is the modified system of differential equations. Basically, the effects are the following. This is K means the level of immunity, which runs between 0 to M, but for the first M-1 level, we have one type of equations, and M means the maximum level of the full immunity here the people cannot get infected. So if you are on the level which is not full immunity, you still can get infected at a certain rate. This is the corresponding vaccination rate. This is the immunity decay rate, which the immunity decay can start. And here you have individuals which come from the upper level of immunity by decaying, going to level K by coming from level K plus 1. Now, on the maximum level, you have no infection, so this term is missing. People can get on this level also by recovering from infection. So from the infection state, after spending some time, you get into this full level of immunity. Here you get in the full immunity level by vaccinating from any other level which is lower. And this is the term which describes the decay of immunity from the maximum level to the previous one. And then the equation for the infectious population reads like this. You get individuals in this highest, this infectious level by infecting from any other level K between 0 and n-1, and the infectious individuals recover at rate alpha and then get in the state full immunity SN. So of course, if P equal to 0, so if you want to have vaccination independent of the population size which is infected, then you set these terms to be equal to 1. Since you have no death effects, also no birth effects, you have a conservation property. So the sum of all components of our system stays always equal to 1, because this was our initial assumption. We scale the variable so that in the full number is, or the full density is equal to 1. Now let's make some assumptions. The beta k, this infection transmission rates, can be also written as a product basic reproduction number Rk times the factor alpha, which is the inverse of the average time spent to the infection state. Now, further assumption which is important for the mathematical properties of the model, for the immunity levels, not the lowest level, but between 1 and n-1, not the lowest level, not the highest level. We can assume that these basic reproduction numbers are less than 1. This means that a partially immune individual does not contribute to an exponential growth of the epidemics. So the average number of secondary infections produced by this partially immune individual is less than 1. This is no significant restriction because we are free to choose our compartment. So we put all individuals from which this R number is less than 1 into a compartment which corresponds to a partial level of immunity. For R0, for the individuals with no immunity, R0 of course can be larger than 1, and this is the significant case because otherwise the epidemics will die out anyway. So you assume that R0 basically is larger than 1, but for all other immunity levels, assume that is less than 1. Of course, for the maximum immunity level, you have no, the beta is equal to 0, we see here. And of course, on this highest level, you have also no vaccination. Of course, the natural conditions are that these rates are larger than 0. Vaccination rates, gamma k, are larger or equal to 0. We can also have the case of no vaccination. Immunity decay rates also strictly positive because immunity is always decaying. And on the lowest level, you have no immunity decay. So this is 0. Now let's give first some technical conditions. What is the stability of an equilibrium? So we look always at the equilibrium solution of ordinary differential equations because they are the stationary solutions, so they do not change in time. But here is now the question, is this equilibrium point stable or not? Being stable, or let's say, as it's the technical expression here, locally asymptotically stable, means that the solution converges to this equilibrium point if they start in a certain attraction range. If it would be globally stable, but this is harder to prove, then all solutions will converge to this equilibrium. This would be the stability, and instability means the solution can also go away. Even if you are close to that point, the solution will diverge and will go into other regions. Now, the criterion is that we consider the linearized system, so the matrix A is the Jacobian matrix of the partial derivatives of the functions of the nonlinear system of the right-hand side. And if these eigenvalues have all eigenvalues have negative real part, then this equilibrium point is locally asymptotically stable. If one eigenvalue has a positive real part, then it will be unstable. This is the criteria. And now let's look at this nonlinear system of equations. This is basically the right-hand side of our ODE system, and we set them is equal to 0. This is also the conservation property which we can use, and I use the conservation property instead of the equation of I. But sometimes in our computations, which I don't show the computations, we can also use the last equation for I. So this are basically the right-hand side, which is set equal to 0, except that the conservation property says that the sum of all components is always equal to 1. Now, this is the Jacobian. I don't explain it, but just the form of it. We have on the diagonal some entries on the upper diagonal here in the last column, and in the last 2 rows are some elements, and otherwise this matrix has all other elements equal to 0, just to have an idea how it looks like. And what we want to analyze are the properties of the eigenvalues of this matrix. Now let's assume first the case P larger than 0, or that we have no vaccination at all. This means that the vaccination can depend on the size of the infected population, or that we have no vaccination. Then we have 2 types of equilibria. The first type is the trivial equilibrium, where there is no infected population. We have to solve this nonlinear system of equations, okay, this one. Set I equal to 0, and let's look first for solutions where we have no infections. Replace all terms with I equal to 0, then this is the unique trivial equilibrium solution. In this case, we have only the equilibrium solution. All people are on the lowest level of immunity, because if they have no infections, they don't vaccinate, and if there are no infections, they don't get infected. So basically, all would stay into the lowest level of immunity, and that's it. But now it's the question of stability. If R0 is less than 1, then this equilibrium is stable, locally asymptotically stable, because you can compute the eigenvalues of this matrix, which I showed you, and they are all negative and also are real numbers. And in this case, we have no other equilibrium state, either with I equal to 0 nor any other equilibrium. But this is not the interesting case, because if R0 is less than 1, the other R's are always are also assumed to be less than 1. So this infection will die out. This is not a dangerous epidemic. So let's go to the assumption that R0 is in fact less than 1. Then we have also an endemic equilibrium, and endemic equilibrium means that we have an equilibrium where the size of infected population is not 0. We have a constant value of the density of the infected individuals. We can prove the existence of this equilibrium, but it's not explicit. So we have here the explicit solution here, but in this case, it can be only proved that there exists this equilibrium. If we have this assumption that all other RKs except R0 are less than 1, then this equilibrium turns out to be unique. And the stability of it is an open problem, because if you cannot compute it explicitly, you cannot have the matrix, the Jacobian matrix at this point explicit, and for the eigenvalues you can not say very much. Now let's assume the other situation, that we have the vaccination independent on the size of the infected population. At least on the lowest level of immunity, we have to assume that we have a vaccination rate gamma 0, which is strictly larger than 0. Then we replace all terms with I to the power p with 1. So we have basically this term for vaccination, just constant rate gamma k on level sk. And here we get, this is the equation corresponding to the full level m of immunity. Now, again, the same 2 types of equilibria. First, the trivial equilibrium. You can compute this explicitly, but I will not give the formula. It's not 1 and 0, 0. Each component is non-trivial, and they can be computed in terms of these coefficients. One eigenvalue of the Jacobian matrix is this one. And for the stability of our equilibrium, it's necessary that this eigenvalue to be negative. This is a real number here. This is a real eigenvalue, and of course, all eigenvalues should have negative real parts. So this eigenvalue should be negative in order to be a necessary condition for stability. Of course, the other eigenvalues should also have negative real parts, but we concentrate for the moment only on this one. So if this condition Sk are the components of the solution at this equilibrium, which can be computed, as I said, and if you write explicitly this condition by the explicit solution Sk, which can be computed, you get this condition. So this term, which you see here, should be less than 0. It looks complicated, but you see here, it depends on the coefficients, basically on the reproduction numbers, on the vaccination rates, gamma j, on the immunity decay rates, eta j. Now let's simplify a little bit and try to make it more understandable. What does it mean? For example, this term is negative when? Well, all Rk are less than 1, because you see here the difference, R0 minus 1, R1 minus 1, and so on. If all are negative, the last one is anyway negative, then it will be true. But of course, this is not the interesting case, because interesting case is with R0 larger than 1. So let's go on to this case. Now assume that R0 is larger than 1. This is the normal case in an epidemics, but all other Rks are less than 1. Now let's go back. All terms are negative except the first one. Of course, the last one we will leave, and the other we can neglect, because they are negative, and a sufficient condition would be then a very simple one, which is this inequality. What does this mean? This is a global inequality which involves all vaccination and immunity decay rates. And what we want to have is, of course, the left-hand side is larger than 0 because it's R0 minus 1. So the right-hand side should be big enough, yes? Either if the vaccination rates gamma 0, gamma j, this is increasing in these variables, should be large enough, or otherwise immunity decay rates sufficiently small. So basically the individuals stay long enough on a certain level of immunity, and this immunity doesn't decay too fast. So it's just a logical condition. So if immunity lasts long enough, or if vaccination is performed frequent enough, then it would be stable. Now, this can be also achieved if all other Rks are larger than 1, but basically no restriction on the Rks. It's still possible to be negative when this negative term is large in absolute value, all other terms being positive, or you can see also here, for example, this vaccination rate gamma 0 should be large enough, then the first term is smaller, even if it's positive, and we assume that the other ones are anyway smaller. R0 is the largest reproduction number. But this is, as I said, not necessary to assume, because we are free to choose our compartments, and we choose compartment or immunity level case such that this R number is there less than 1. Now, what about the other eigenvalues of the Jacobian matrix? They are the eigenvalues of this matrix, of this type. Doesn't look too nasty in this case, but we can prove that they have negative real parts using the Routh-Hurwitz criterion. I don't get into details. You can prove it that for m equal to 2 and m equal to 3. Probably it's true also for larger m, but the calculations are complicated, because here you have to compute a characteristic polynomial explicitly, and you have to get some properties of certain determinants. So what does this mean, m equal to 2 and m equal to 3? Basically, in these cases, this trivial equilibrium is locally asymptotically stable, meaning that this inequality is fulfilled. For example, if you have states like this, no immunity, partial immunity, full immunity, or for m equal to 3, no immunity, low immunity, high immunity, and full immunity. This is reasonable to assume. M equal to 3 seems a reasonable case. For larger than 3, maybe if you compute long enough, you will get it also for m equal to 4, but of course the general question is interesting, how to prove in the general case. Now let's go to the endemic equilibrium. It turns out that this exists only if the trivial equilibrium is unstable. So if this trivial equilibrium is stable, meaning that if this condition is fulfilled, then there is no other equilibrium than the trivial one. Here we can also prove existence but no explicit solution. Uniqueness is guaranteed by this condition, and the stability of this is also an open problem, because you don't know its explicit form, you don't know the explicit value. Now let's summarize the results, but only in the relevant case that R0 is larger than 1 and all other Rks are less than 1. First case, vaccination dependent on I, so if I is low, also vaccination rates are low, or no vaccination at all, then you have, in this case, a unique trivial equilibrium, but this is unstable. So basically, the epidemics won't die out, but the solution would go, at least many solutions, because you don't know the global stability, only the local one, would converge to this unique endemic equilibrium. So with an I value of I of infected population larger than 0. So the conclusion is here. In this case, it's not possible to eradicate the epidemic, because this trivial equilibrium is unstable with I equal to 0, and you will have a stable, at least locally, endemic equilibrium. Now let's take the other situation when you have vaccination rates independent on the size of the infected population. So we have a unique trivial equilibrium. Trivial, I mean, I repeat, with I equal to 0. It's unique. The necessary condition for stability, so one eigenvalue to be less than 0, because this is a real eigenvalue, is this one. For example, this holds if we have this inequality. So basically, in this case, you have no endemic equilibrium. It's theoretically possible to eradicate the epidemic. This is stable, at least if m is less or equal to 3, so on the levels which I explained previously. Theoretically, the eradication is possible, but when the immunity decay rates are sufficiently small, so if the individuals stay long enough into a certain level of immunity, or the vaccination rates are sufficiently high. Now, this is a theoretical result. Practical, there are some limitations because the immunity decay rates are given, you cannot change them. And where you can change something is the vaccination rates, but also there you cannot change at arbitrary, because you cannot vaccinate too frequent. So this is also, from medical reasons, not possible. So in practice, you have to know these parameters. You have to know the rates of decay of immunity, and you have to know how frequent you are allowed to vaccinate, because you cannot vaccinate every month or so, or every 3 months, or every half a year, maybe once a year, I don't know. It depends, and that's why also in this case, it's not guaranteed that the epidemics will be eradicated. Theoretically, it's possible, but in practice, the result depends, the answer depends on what is the relation between these coefficients. Now, if the necessary condition for stability is not fulfilled, so the trivial equilibrium is in that case unstable, then there exists a unique endemic equilibrium with I larger than 0. Also in this case, so you cannot eradicate the epidemics also in this case. But of course, the stability is an open problem because you don't know the solution explicitly. And this is just a summary comparing the two situations. In one situation, if you don't vaccinate at all, or if you vaccinate just where the size of infected population is large, then in any case you cannot eradicate the epidemic. In the other situation, when you vaccinate independently on the size of infected population, theoretically it's possible. Practically, the limitations are given by the immunity decay rates, which you cannot change, and also the vaccination rate you cannot increase arbitrarily. So the answer here is open. It depends on the coefficients. And this is the last slide. Thank you for your attention.